So, oh yeah. So one of the things that ticks me off about Python is because it's an interpreted language, and this is related to what I replied to you with, is, and we had mentioned it here in class as well, that we have these compiled languages like Java, C++, C Sharp, yada, yada, yada. And then we have a zillion different interpreted languages, because interpreted languages are much, much, much easier to write. Python, JavaScript, um, Go, which is Google's language. I mean, there's a huge list of interpreted languages, because writing an interpreter is a whole lot easier than writing a compiler that converts high-level code into individual instructions for a CPU. Well, so then what happens is, if we look at strictly from like the machine learning or data science type of tools, a lot of them are written in Python, because in those fields, sometimes the people working with it are less programmy and more, hey, we can handle 5 lines of code, but mostly we're bringing in data sets and then visualizing them and seeing what we see. It really isn't the best language for it, because what's under the hood is like, I don't know, a 4-cylinder engine that you're trying to pull a camper with. You know, it's that kind of analogy where I feel like they go to the Python side out of convenience rather than it being the right tool for the job.
Yeah, I was like researching a little bit. Like a lot of people like suggest that it's not like much of a priority to learn.
You know,
they're like interesting.
Well, I think it's less about the priority of learning languages and more about the number of people in the workforce who are using programming languages of some form has increased. You know, if we roll back 15 years ago, the only people that use programming languages were software engineers. They don't need friendly, fuzzy programming languages,
Yeah.
right? But if you have business analysts or data scientists who, I mean, your whole career is focused around the idea of asking the right questions and then looking at data and drawing conclusions from it. But now it's like, hey, if we can give you a tool that lets you write 5 or 6 lines of code to load in the data set and start doing visualization stuff on it, now we have a whole lot more people who are using programming languages, not using them at a really deep level, but you need to make them accessible to a larger group of people. So, you know, I think it's good for maybe society, because basically everybody at some level is a computer scientist now, right? In almost every industry. There is something where you have to do something beyond like a word processor on your computer. So that's where I can maybe get behind Python as a, I don't know, as an okay type thing, but it really surprises me that it didn't go the way of JavaScript, which has been around forever, and just letting them write it in web pages and move on with life. Because you guys are probably using Anaconda for your Python installs, or are you using some online thing? Okay. But there's this whole big application called Anaconda, which is in the machine learning and data science area, where you download Anaconda and you install it. It basically has all the plugins for that world. You know, and it's convenient for that world.
You just use Google Colab after installing it.
Yeah. I mean, which is no different than like the online GDP thing we use. It's better than it really should be, to the point where sometimes you can just use it instead of using a local IDE. I do it all the time because I'm always switching between machines and stuff, but yeah, I don't know. Let's see. We were talking about classes, right? And if I recall, I left a bug in my code to remind me where we were starting. Does that sound fairly accurate? All right. Did you? Oh, got it. All right. Get that. Oh, doesn't look like I left an error in there. I thought I did. No. Well, whatever. All right. So last time we started introducing the there was no homework, right? Okay. Man, so what did you do with your time? Yeah, so over the last couple of classes, we've been transitioning between different ways we can represent fractions as our example in a programming language so that we can work with them. We started off with 2-bucket arrays, we call those vectors. Then we transition into this idea of a struct, which allows us to have a single variable type to hold multiple values. Was reasonably convenient. But then that guy had the side effect of, sure, we were able to store our numerator and denominator inside these fractions, but we still have this giant pile of functions laying out here in the in the street. So that goes back to first couple of weeks of class when we were talking about the difference between procedural programming languages like C and object-oriented languages like C++. And I used the example of the procedural versus object-oriented telephone, where the procedural telephone looks like a giant pile of wires, even though upon closer inspection, you are convinced that it is in fact a telephone. And the object-oriented telephone looks like a phone, even though we know all those wires are packed inside one way or another, right? So now we're moving in that direction. So let's look at it as upgrading our structs to a class example, with the caveat. I think I mentioned this last time, and it's really it's more set in stone in newer languages like Java and C#, but the default behavior of it in C++ is consistent with that, and that is that structs by default are passed by value. So we have to choose to pass around pointers to structs in C++, whereas objects by default are passed by address, because when we build an object, we are building it with a pointer in mind. All right, you would have to go out of your way in order to get a non-pointer based instance of an object. All right, and you're going to hear me say that word pretty often, so let's go ahead and get a definition of it. Instance. Let's call this instance of an object. So whenever we create a variable of an object type, that is called an instance of that object. Okay, real life example of this: if you go out and buy 2 iPhones, you have 2 instances of the iPhone, right? Okay, somebody had these blueprints or whatever for building an iPhone. They used that blueprint, which is like our code for our class here. This is our blueprint for how to build a fraction. And then, so they used the blueprint for how to build an iPhone, and they used it to produce 2 physically separate iPhones. Each one of them is an instance of an iPhone. Make sense? All right, so that's what that word means, instance. All right, and it's important to keep that separate. We're going to stumble upon this sooner rather than later, but we don't always use objects as instances. Sometimes we will create an object that is meant to be used as like a single entity. I don't know, maybe trying to come up with a real life example of that where we wouldn't have multiple versions of something. So let's use I don't know, like the St. Louis Arch or something. It exists once. So they had a blueprint, they built it one time, and if you want to do anything arch related, you have to use that original one of a kind type thing. So sometimes we'll build objects with that in mind, and a lot of times they follow something that's a design pattern called the factory design pattern, where you have this one entity, and whenever you need something done, you just go and use the same thing. You don't create multiple instances of it. And we'll stumble upon examples of that, but don't necessarily lock yourself into thinking that every single time you create your own object, it's for the purpose of creating instances of it. Most of the time it will be, but there are plenty of opportunities where you might say, hey, I really need a class that houses a whole bunch of math functions, for example. And because of that, I don't need to create multiple instances of that, but I'd like to say Mike's math class dot absolute value, Mike's math class dot sign. You know, you have all these different functions. You don't need multiple copies of those. You just need it housed somewhere so your main program doesn't have 4 zillion functions in it. Okay. All right. So we talked last time about the idea of these header files. So these guys allow us to describe what our class will be. So in this case, we're saying a fraction will have 2 public fields. I'm going to be making those private soon, but we're going down the path of understanding what the difference between public and private is. So I'm going to create 2 public fields called long numerator and long denominator. And then we have a constructor. Remember, the constructor for a class always has the same name as the class in just about every object-oriented language. Anybody remember the language I said is different than that? Objective-C, Apple's older language, which I actually kind of prefer, but kind of the reason being in Objective-C, typically we would say for fraction, the constructor might look like init with numerator, long num, and denominator, long denom. It would look something like that. We are writing the constructor, and I just like the way these read, even though it does feel much more verbose. Oh, I'm sorry. This is usually, I mean, you could just bang on the keyboard, name your constructor whatever you want, but typically naming convention in a language like Objective-C has your constructors named something like init something. If it's a generic constructor that doesn't require any inputs, maybe you just call it init. Otherwise, you're saying to build a fraction, we initialize it with a numerator and with a denominator. So it kind of spells out that whole thing, which then allows us to maybe have variable names that are less, I mean, nothing keeps us maybe calling this N and D, because we don't need the variable names to be overly descriptive because we've really described it as part of the syntax of the function. I actually prefer this type of thing. And I'm going to, well, here, let me leave it in this format for right now, because I want to really compare these two to each other. So this is going to end up giving us an error later on. So remind me that I've done this, but I do want to compare the two because it is instructive. All right, so we have this constructor, and the job of a constructor is to initialize an object to its initial state. Okay, whenever we create an instance of an object, we always use the constructor to build that instance. All right, and here I'm going to throw one other little thing on here. All right, so remember, the header file is kind of where we prototype the stuff. These are our, this is what we're going to be writing. And then we actually go and write it in the CPP file. Nothing actually keeps you from putting everything inside one file. But if you do have multiple things like main, we're probably going to be defining some fractions here in a few minutes. So both main and fraction CPP need to both be aware of fraction HPP. They need to know what are the things fractions can do. Fraction CPP is where we're actually implementing those things, whereas main, we're going to be using those implementations. All right, so that's why it makes sense to have your overview of your class in its own separate header file, so that when you include that header file inside of other classes, it's not bringing in some gigantic implementation with everything under the sun. Instead, it's bringing in just enough information to let the compiler know that what you wrote is legal code. Because when you compile the whole application, it's going to get linked to assembly code that knows how to do those different things, and you only need those to exist one time. All right, so we'll go into our fraction here. We'll start implementing these guys. So remember the way we link. So notice here in the fraction CPP at the very top, we're including fraction HPP. And reminder here, when you have stuff inside of double quotes instead of the angle brackets, remember when we do something like include IO stream, something like that, the angle bracket things we see here means that it's built into the language, something you didn't write. Double quotes means look in the current directory. It's one of my things. Make sense? That's how we differentiate it. All right, so we use the name of the class followed by it's a object-oriented thing, two colons to link it back to the fraction HPP. So we're saying we are going to implement this constructor, name fraction that takes two longs as parameters, and we want to link it back to the fraction header file because we're filling in the actual implementation for that guy. And what does it mean to initialize a fraction? Well, it means take the numerator and the denominator that were passed in and set the internal values. Now, at the end of class last time, we mentioned that we initially cheated, right? And we had this being long num and long denom. That way we can say numerator is equal to num and denominator is equal to denom. This has to do with scoping rules. And the unfortunate truth is if you walked into a software engineering team today, you will find programmers that still write their stuff this way because they don't understand the concept of this keyword that we're going to talk about. And that is pathetic. And this is happening in professional software development today, unfortunately. And the thing is, it's because they learn through trial and error. If they said we're going to take in variable names, numerator and denominator, and then they say numerator is equal to that, denominator is equal to that, and then all of a sudden they don't get the behavior they wanted, because what they really want to do is they want to set the numerator right here equal to the numerator that was passed in. Yet saying numerator equals to numerator, variables always resolve to their most local definition. So the most local definition of numerator is this guy right here. So we're basically setting that variable equal to itself, which has zero impact on the numerator owned by this class, this instance of a class. So what do? Rather than learning how to do it right, they just shorten their variable names. It's like, poof, now they're different. So now they don't have that bad side effect because now numerator, my most local definition of numerator is one of the fields in my class. And my most local definition of a variable named num is this guy that was passed in right here. So they just do it until they stop getting errors, is the problem. All right. Where I've made the argument that it's probably never a good idea to not name your variables something meaningful. So what ends up happening? We have this, I think I introduced it at least at the end of class last time. Okay, so let's throw. We have this keyword called this. This is how, here, I'm going to maybe put it in quotes or something. This, killing me. You have to capitalize everything. Is how an object, well, let's say an instance of an object refers to itself from within itself. This is the same concept of when we're talking about something about ourselves, we usually say me or I. We don't say Mike, right? We say my car, my house, my hair, yada, yada, yada. All right. So this is how an object can refer to itself, how it effectively says my stuff. Okay. And then we can further spell this out and say this I would think after you backspace once, it would like holds a pointer to the place in memory where this object actually exists. All right, so that's what this keyword actually holds. That it's a variable that has that value. Now, remember back when I originally said why I use C++ rather than a more modern language, and I said it because it hides less stuff from you. Java hides a lot of stuff from you that I promise is still there. Well, unfortunately, here's an example where C++ does hide something from you. It's how did this keyword get created? So if I'm going to name my parameters coming in here as numerator and denominator, and I want to have the ability to differentiate between this local variable numerator and the variable owned by this particular instance of a fraction, I do something like this. This numerator is equal to numerator. This denominator is equal to denominator. So if I'm sitting inside the fraction, if I identify as this instance of a fraction, I'm saying my numerator equals whatever you passed me. My denominator equals whatever you passed me. Make sense? Just instead of saying my, I'm saying this. All right, but what we don't see here, and I mentioned here on this guy that this holds a pointer to the place in memory where this object exists. That's why we're using the arrow here, right? As opposed to that. As opposed to resolving the value that lives at address this and sets its numerator equal to something. So this isn't new. This is the same thing we were doing with structs and before. All right. The issue we run into here, though, that I don't like in this particular case is where did this come from? Just magically appeared. You know, we didn't define it in here. We didn't define it anywhere else. So let me give you a little context for this. First of all, how are object-oriented languages built? They all follow the same pattern. So in this case, we're creating an object here called fraction, right? Now, from our perspective, fraction is the first object. All right. But what is an object? Well, at the very least, we see that all objects have a keyword called this that came from somewhere because we didn't make it, right? In every object-oriented language, there is a top level object. Usually it's called object, something like that. So, and this follows something called the inheritance model. And we're going to learn about inheritance in here, where maybe we create a class called car or automobile. And then we use automobile as the base for maybe a car and a truck, something like that. So we only write the stuff inside of car and truck that further differentiates it from an automobile. And what do we have inside of automobile? The stuff that further differentiates it from a generic object. All right. So built into C++, there exists this thing that is a generic object. It's the, I don't know, let's call it the minimum amount of information required for an object to exist in the language, whatever that is. And then what we're doing is we're saying, okay, well, I want to have my own more specialized object. And I want this object to be everything that a generic object is, whatever that means. but I also want it to be able to do some numerator and denominator stuff, since ultimately I want this to be a fraction. So I am differentiating my fraction class from the generic object class. Make some sense? But every object-oriented language will have some top-level class like this that has some stuff in it. We go and look Java object. We talked about the so first of all, well, actually, let me show you Java strings. So you'll see what I mean here. All right. So here at the top, it's showing us something very similar to what I've done here. It's saying, here's the string, and this guy came from something called an object. What's an object in Java? Well, it already exists in the language. It's not something you built. And an object has these things. One of them I've actually referenced in class called clone, because Java doesn't have syntax for pointers. So we can't pass something by address, and or by we can't pass something by, we can't pass an object by value in Java. Java makes the decision that if you're going to pass an instance of an object, it passes it by address. But if I, for whatever reason, want to send something and allow the whoever received it to make changes to it without it impacting the original, I can tell an object to clone itself first, which just makes a copy of it in memory, and then send them a pointer to the copy. That way, any changes they make here won't affect the original. Make some sense? So that ability here in Java is one of the things built into every single object. Every single object knows how to create a copy of its memory, among other things. So there's other crap in here that objects know how to do. But you see, it's a relatively short list of things. Okay. So in our model here, we're creating a fraction which automatically inherits from the generic object class in C++. If we were doing this in Objective-C, the object class is called NSObject. Remember we talked about that story? Next computers. So even today, it's still there inside the language that Apple died a long time ago. All right. So we always have this hierarchy, and when we invent our very first object, like we're doing now, fraction, it gets a whole bunch of generic object stuff. That is how object-oriented languages work. All right. So what's actually happening here, I'm going to put a couple of invisible lines of code, is we have something called super is equal to a new object. Actually, I'm sorry. We're going to say this is equal to a new object. And then I'm going to return this. And this goes back to what we mentioned last class, in that constructors do not have a return type. Whereas other methods that we might write, so for instance, we are going to have a collection of methods in here, and we might have a method called that returns a fraction pointer, maybe called add fraction, and this guy takes a fraction pointer f as a parameter, something like that. So this is a method, and methods do have return types. Constructors do not have a return type. Why? Because the return type of a constructor is always a memory address. It's always the same thing. We don't get to specify, because it's going to be a pointer to where this particular instance lives in memory. And we have a couple of hidden lines of code in here where the keyword this gets its initial value. So this fraction starts off as a generic object. Then we differentiate it a little bit from a generic object. Then we ultimately return the memory address of this particular instance. That's what's happening in every single object-oriented language. If we were in Objective-C, which is why I wrote it this way. See, if we used Objective-C as our teaching language in here, you'd be pining for C++. Objective-C has a lot of extra crap. All right. If we were doing this in Objective-C, it would look something like self is equal to, actually, it's that. Then we would say something like self dot numerator is equal to numerator. Actually, in this case, n. Self dot denominator is equal to d. Return self. Self is getting returned as the return type of this constructor, which is just the normal method from an Objective-C perspective. It just happens to return an ID, which is a void pointer in Objective-C, a pointer to someplace in memory. All right. But in Objective-C, we actually will write that line. We will actually write this line. So, and 100% of constructors in Objective-C will start with a line like this and will end with a line like this. They will always end with this line. Exactly. They could call a different constructor of the parent in the event that the parent was, like I used the example a few minutes ago of automobile and car. So when you're creating a car, the constructor that car would create is its parent, which is an instance of automobile. When automobile comes into existence, it would call the constructor of its parent, which is object. Okay, it would just keep climbing up the hierarchy. But in Objective-C, they make you write these two lines, even though every single time you create a constructor, you're building the same sandwich. Make sense? But you get to see what's happening behind the hood, under the hood. Whereas in C#, or I'm sorry, C++, we don't actually write this line. It's assumed to be there. We also don't actually write this line. It's assumed to be there. That's why constructors don't have return types, because they always boil down to a memory address. And that's actually further driven, that point's further driven home to us. If I'm in main here and I want to create one of my fractions, I would say fraction pointer f is equal to a new fraction like that. This is how we'll actually build our fractions here in a few minutes. And remind me, what's that new keyword? We talked about that. You had to give me a definition of the new keyword. What would you say? Yeah, it's I usually talk about like it's the real estate agent, right? New keyword goes and finds RAM for us. Okay, it's the less scary version of malloc. Memory allocate. Objective-C even drops the M. It's just called alloc in Objective-C. So bottom line is, if you are looking at a line of code and you see the keyword new, memory is involved. Pointers are being created, okay? Because that guy finds plots of land and gives you the address where it found it. All right. So here is my call to that constructor, passing it two parameters, a numerator and a denominator. So what's happening right here is a call to this code right here, the constructor. Make sense? And constructors always need to have the same name as a class name. And constructors always will follow the new keyword. That's a true statement in C++. in Java, in C#, really in all modern languages post C++. Swift, same thing. Actually, I lied. In Swift, they actually dropped the new keyword. So you can just say that. The new keyword is assumed. So that's what keeps happening with these newer languages. They keep dropping things that are stuff that the programmers have to type every single time. And that makes some sense from an optimization perspective. If you always are going to type the same characters every single time you write this line of code, wouldn't it make sense to just not make you use those 7 keystrokes or something and just make that piece disappear? That makes some sense, right? But it starts getting to the point where the code's no longer readable. Like I think I made mention in here that the Swift programming language allows you to have variable names with emojis. Yeah. Like I'm talking about how important it is to have like meaningful variable names. Yet in Swift, you can actually have a variable name that is an emoji. Like that's where we're spending our time, is saying, well, we need to have that. Nonsensical to me. All right. So questions about, well, and you see the other interesting thing here. In Objective-C, it's not the this keyword, it's called self. Remember, I've talked about this as how an object says, talks about themselves like me or I. In Objective-C, it's self. In Java, well, in C++, it's this. In Java, it's this. In C#, it's this. In Python, it's self. Okay, so you go way back, Visual Basic, which isn't really used anymore, but Visual Basic, its version of it was called me. I'm actually surprised that one didn't take off, because that's really the one that fits the purpose the best. If it's how an object refers to itself from within itself, and we're kind of, treating it an instance of an object like a person, the way it would talk about itself is by saying me or mine or that kind of thing, right? No, it never took off. Language just died off and nobody took it. All right. But whenever you see the keyword self in any programming language you work with in the future, it means the identical thing as the thing this. That's just the syntax for that language. All right, these are how objects refer to themselves within themselves. And that's going to be a very important concept. So somewhere in your head, earmark that as extremely important that you understand that connection, because we're going to be using it a lot. We've already seen that we're using it inside of the constructor here, where we're saying this particular fraction's numerator is equal to whatever numerator that was passed in. This particular fraction's denominator, the one that I'm building currently, has its denominator set to whatever denominator was passed in. Because when we create fractions, we want to create multiple instances of fractions. So if I go out here and I create a fraction pointer F2 and say this guy is a new fraction, what about 3/4? What we've been using as our example, like that. F is an instance of fraction. F2 is an instance of fraction. If I am inside of this constructor, the keyword this will hold the same memory address as F will ultimately hold. So externally, because remember, the definition of this is how an object refers to itself from within itself. Okay. So here, let me just dump some stuff so we can start experimenting with this to drive these points home. Let's rewrite all that. All right. Don't you love that when he's like he said he spent 60 hours in his homework last week, and it's like we just delete huge pages of code. Like that's just gold. We got to rewrite that. Good practice. All right. Well, let's get rid of some of my other crap. So I no longer need any of those things, right? I no longer need this guy. Look how much better main already looks. So clean and fresh because we're going to hide all those wires inside of this guy. See where we're going with these connections? All right. So I'm going to kind of prove something here. I typically prefer to put all of my includes inside of the header file rather than inside of the CPP file. That way up top here, it's very minimal. So, but here's the reality of the situation. I want to come in here and do something like C out this and out. I want to output the value of this, which is going to be a memory address, right? And here I'm going to actually put inside the constructor that. And then out here in main, I'm going to say F outside the constructor. Make sense what I'm doing here? But now in order to have access to C out, I need the IO stream. We can go ahead and say include IO stream here. And then if we don't like having to do that guy, by the way, notice we've seen that syntax before, like we saw right here. C out is a function that is owned by the standard library. Make sense? So we've seen this before, and it's been implemented as an object-oriented standard is an object-oriented thing. But in any case, we typically will say something like using namespace standard, which then means we don't have to say that. Make sense the difference? Because sometimes you'll find code examples on Google, and a lot of them will still say the standard : thing. That's the difference, whether or not you said you're going to use that namespace, which if you're going to be using a lot of C outs or other stuff from a standard, you might as well say using namespace. That way you don't have to type std : a zillion times. All right. Okay, so inside of this constructor here, what I was getting at is when I write something like this, I would typically hide those things inside of the header file. But the reality is you only need the includes inside of the header file that you're actually going to use inside that header file. And the reality is since we're not implementing anything in here, we're just prototyping, we are likely not going to be printing anything out to the screen, right? So we're likely not going to need IO stream. So you would probably say, I'm only going to bring this into existence at the time that I need it. And that's fair. That is a reasonable thing to say, that I'm not going to just front load it. I'm only going to bring it into existence when I need it. I tend to like to put all my includes and stuff inside of the header. That way my implementation, which is already going to be messy, looks cleaner. But I think you could really go either way. Even as I'm saying it out loud, I'm not sure I can make a super strong argument for it. So here, let's just put it in here and let's see how it makes us feel in 10 minutes. If I start getting nauseous, then we'll move it back. Let's get very passionate about coding, right? This is so fun. All right. So what I want to do is inside the constructor here, I'm going to go ahead and print out to the screen whatever the value of this is. And we saw that we didn't create this variable this. I'm telling you it's something that happened behind the scenes. We also didn't return the value this. It's something that's happening behind the scenes automatically. Objective-C would have made us write it. But all we're doing is we're setting our numerator and denominator here, and then we're going to output the current value of this. And the current value of this is the same whether I do it before or after setting the numerator, because this is just the memory address where this dude lives. So that constructor will get called right there. So we're going to see the memory address of F. And here, let me just comment out F2 so we keep it as clean as possible. So inside the constructor, we're going to see what the memory address of F is, or of this. Outside of the constructor, back here in main, we're going to print out the value of F, which is going to hold the memory address. One, because we've said it's a fraction pointer, and two, because we see the new keyword hanging around. Lots of evidence saying this is a memory address if it's not a syntax error. And what we're going to see, fraction was not, oh, gets back to something I said earlier. Why do we have a header file and then our implementation? The implementation needs to know about our fraction. Main also needs to know about our fraction. So I'm in main CPP here. Both of them need to know what fractions are in order for us to start using fractions. They don't need to know about the implementation. We can put all the implementation for fraction stuff inside of the CPP file for fraction. But that's why we have header files being self-contained. So this is just the information the compiler needs in order to make sure it can check to see that you've used fractions correctly. What didn't you like? Oh, I still have that in there. Remember I said it's going to cause an error? All right. That guy out. I did it again in here. Okay. Ta-da! All right. So right off the bat, what do we see? The same memory address. Make sense? This is how an object refers to itself from within itself, in this case, inside the constructor. Why do we need something like that? Because inside of this constructor, in our current example here, we don't know about the variable F. F is not in the scope inside here, right? If I start talking about some variable named F, which only exists out here in main, this guy right here, we start talking about that in the constructor will be like, I've never heard of this guy. Make sense? So this is a scoping rule thing, and we're going to say, hey, it's probably going to be reasonably often that while we are inside the implementation of an object, we're going to have to talk about ourselves, either talk about functions that we have in here, talk about fields that we've written, whatever it is. All right, make some sense? All right, so that this keyword is a super important concept, and it's also a concept that is sometimes a little difficult to wrap your mind around. So hopefully this gives you some context for that, where I've printed out the keyword this inside the constructor, and I've also printed out the value of F outside of the constructor where we're using that fraction, and we see we get the same memory address. These are synonyms for the same place in memory. Questions about that? Coffee, so sad. All right. So now, let's get rid of some of this stuff. Here, I'll comment that guy out, and I'll do the same thing inside the inside of main, just in case you want to uncomment that and see the refresh your memory about this keyword. Okay, so now we want to go ahead and teach fractions how to display themselves, maybe, right? Because we're really trying to build out the same thing we had before, except we want to put all those wires inside of the class. So out here in main, it's, you know, clean. So we'll go into our header file. And here, I'm just going to change this guy to display. All right, so and this guy's not going to return anything, right? Display is going to print something to the screen, display the current state of that fraction. All right, now I'm going to go and implement this guy. So inside of the fraction CPP file, I'll go ahead and paste it in there like that. Quick rule of thumb, common mistake, at least a common mistake that I do, is sometimes I'll forget to link this to the header file. If you forget to link it to the header file, you're going to get an error. It's going to say fractions I haven't heard of this guy. I'll produce the error for you here in a minute. All right. So then what are we going to do inside of display? We're going to say cout this numerator followed by slash followed by this denominator. All right. So once again, inside of the fraction class, we are talking about this particular instance of fractions numerator, this particular instance of fractions denominator. The name of the function is display. Notice it takes no parameters. The display function we wrote before took a fraction in, right? Took a struct fraction. This guy takes nothing. He doesn't return anything. Why? We know all the information about the fraction that was used to call this version of the display function. So now to use this guy, we'll come out here to main. And I'll go ahead and say F, you call your display function. F2, you call your display function. F is an instance of the fraction class. F2 is an instance of the fraction class. They both have a display function, but they both have their own version of the display function. F's version of the display function has a variable available to it called this that knows where F lives in memory. F2's version of the display function has a variable named this that knows where F2 lives in memory. Go ahead. See, I was testing him. He started for the day. I always put little purpose sprinkle typos in there. Oh, I forgot. Thank you. All right. So this is how we call the display function of a fraction. We don't need to pass in the fraction we want to display because we use that fraction to call it. This is F's version of display. This is F2's version of display. We go to run this guy. Oh, I wrote it out of order here. The return type comes before the linking. Ooh, like that. This. So there is F displaying itself. There is F2 displaying itself. Make sense? All right. So now let's talk about the problem with these public fields up here. I'm going to go ahead and after this guy, I'm going to go ahead and say F numerator is equal to -2. F denominator is equal to, I don't know, 14. And then we'll say F dot display. We have externally modified the internal workings of F. So public, private, there's a third one called protected that we'll talk about when we get into inheritance. They are there to tell us about the ways that the values can be accessed. So we're going to call this guy object member security. I'll say remember the members of an object are fields, constructors, and methods. Those are the different kinds of members of an object. And when we use these security things, we have public, private, and protected. And they're all lowercase. Right now, we're just going to say to be determined for protected because I don't have an example to give you since we haven't done inheritance yet. Okay. Public means that this member is available anywhere that this class can be seen. Make sense? So if I know about the class inside a fraction, and I know about the class inside a main, I can access the public members from any of those places. We go back and look at our fraction here, we notice our public section has our fields and also has our constructor. Now it makes sense that we want to be able to access our constructor from out there, because if I didn't have access to my constructor over here, I wouldn't be able to build fractions. Definitely need that guy. Now, we might decide that, look, the way that fractions are built are through this constructor, or possibly if we want to be able to change a numerator and denominator, we should provide ourselves some methods for making those changes. Okay. What we don't want to have happen, likely, I mean, it's legal, but probably isn't good programming practice, is we don't want to let external entities make internal changes to our objects. So usually what we make private is the fields of our objects. So if I go and do that, if I just change, I'm going to move public down to here. And then I'll make this the private section. So now our fields are private. If I try to run this guy now, it's going to yell at me saying that numerator is private within this context. So let's give a definition of private. Private. Killing me. Be better. There you go. Means that this member is only accessible from within this class. Actually, well, I'm going to write this a little bit different. Accessible from within here, I'll just put a little caveat. Within this class, including other instances of this class. And you'll see what that means here in, well, here, I'll just kind of say it out loud because it's probably going to end up being part of your homework. For example, when we go and write a method called fraction pointer add. And this guy takes a fraction as a parameter. Inside of this add function, we can refer to this particular fraction's numerator and denominator, but we can also refer to F's fractions numerator and denominator. Both of these things are allowed here, even though we are currently inside of whoever owns this particular add function. So whatever instance of fraction called this function, that is who this is. And these guys both have private fields that are only accessible within the class that they were created in, which is the fraction class. But that is not to be confused with saying they're only accessible within their own copy of fraction. If I am inside of the add, so I'm inside of fraction.cpp, that file, I can access any fractions, numerator and denominator, as long as I have access to the fraction. So it doesn't lock down fractions from other fractions inside of the implementation of fraction. But what it does do, I'll just keep this blank for now. Here, let me actually comment that out as a hint for the homework. It doesn't make the homework that much easier. It just keeps you from having to do one extra little thing. So now what this guy does, we'll go ahead and run it again so you see it. It's complaining that we cannot access this numerator field inside of main because it is private and we are not inside of fraction.cpp. We don't have access to private members of the fraction class outside of fraction.cpp. So this makes our numerator completely hidden from us outside of the fraction class. It's security, right? We don't want to let external entities make internal changes to our fractions. Now, could you see a world where you might be interested externally in knowing what the particular fraction's numerator is, or what this particular fraction's denominator is? You might want to know those pieces of information. Not necessarily be able to change those pieces of information, but maybe read-only access, something like that. So what we can do is we'll add some more methods. We're going to say long get numerator, long get denominator. And you can name these whatever you want. This is just usual naming convention, calling it get something. And these are in the public section, so we would have access to these inside of main. Go ahead and write these couple of guys right here. Here, I'll simulate an error here in a second. Return this dot numerator. Return this dot denominator. All right, so I have a couple of functions here that get the numerator and get the denominator, but notice I have forgotten to link it to my header file. Common mistake, okay? So by doing that, let's go back to main here. We no longer can do this, but we already saw that. Since those members are private, we can't do that stuff. So we'll come back here. I'll go ahead and just run this. It'll give us the error. All right, it says invalid use of the this keyword in a non-member function. So we're in fraction CPP. it says, hey, you can't use the this keyword. I'm like, well, why not? I'm inside a fraction CPP. The this keyword does not exist in this scope because this function is just a function living out in the middle of nowhere. It has not been linked to the fraction class. It doesn't know that we've implemented this as a part of the instance methods of the fraction class. Therefore, it doesn't have anything access to any of the instance variables, including this of the fraction class. So I'll go ahead and put that guy there. Remember, it's after the return type. Okay. Oh, I didn't do it. It's complaining right now that my add function doesn't have a value returned. I've written it to return a fraction pointer, yet I haven't finished implementing it yet. But in any case, out here now, I could do something like cout f get numerator, which should be a 1, right? And now I see that I can now access the numerator of that fraction f, or fraction f2 if I want to call that one. I can access it as read only. I cannot use that function to change it. I can't say f get numerator equals 7 or something like that. I can't try to use a function that returns a value to magically internally set some internal thing. If I wanted to be able to externally set the numerator, I could write a function like set numerator. So I can come in here. I can do something like, let's just steal this guy. And for setting it, it's not going to return anything. Oh, and this guy's going to take in a long, we'll call this guy new numerator. And we'll say this dot numerator is equal to new numerator, something like that. Now, why would we have a getter and a setter? That's what these guys are called. Written like this rather than just make those fields public. Because as of right now, I have the ability to read my numerator. I also have the ability to change my numerator, right? So if this is where I leave it, I might as well have made it public because I have the ability to read and write it. But what you can do in the event that you want to have something like this that lets you set something externally, you can now maybe wrap this in an if statement so you conditionally set it. Maybe we don't want them to set the numerator to anything less than 1, for example. We only want positive things, and we certainly don't want the denominator to be a 0. Then you got that divide by 0 thing and the world shatters. So I could do something like if new numerator is greater than 0, only under that condition do you get to update the numerator. So this allows you to conditionally set values inside of objects rather than just have it be a free-for-all externally. Make some sense? All right. Now, the reality is, in our current example, we probably don't have a real great use of needing to have access to our numerators or our denominators directly outside of the fraction class. But we'll leave it there as an example. Make sure this guy still runs. Oh, I said that here's the thing you can't do. You can't use that guy to do that. Clean this up a little bit. Okay, got it. So we're back to a stable state. So your homework redo the struct implementation for fractions to use fraction objects instead. All of the fraction functions should live within the fraction class, and main should just use those fractions to do the logic. So we already have display. So fraction should contain a constructor, which we already have. Should be able to display itself. It should be able to add itself to another fraction. And we have a starting point for that, right? I wrote the function, but none of the implementation yet. It should be able to reduce. So this should change the current fraction to its reduced form, not return a new fraction. And then somebody remind me when I'm solving this next class that I make it do work that way, because I think I had asked for that in the last assignment, but then the example I did in class returned it. Anything else it needs to do? Oh, this should use the Euclidean algorithm. So build it, display it, add it, reduce. Did our previous homework do anything else? I think that was it. Okay. And I will give you the starting point code from here. So given this dude, and then submit a link to the code and the self-assessment.